Alright, so today we're going to talk about the principle of least action, which is probably my favorite physics topic. So before we get to talk about it though, we need to talk about constraints and coordinates, because those are going to make the problems that we're going to want to eventually solve a lot easier. For any given mechanical system, it can usually move in a variety of directions, but it's generally constrained in some sort of way. So if you think about, for example, for a concrete example, like a pendulum with length L, then this pendulum is constrained so that it only swings about some angle theta. So we would say that theta is going to be what's called our generalized coordinate. The generalized coordinates of a system are just going to be the smallest set of coordinates you need to fully describe the system. Because, for example, since this pendulum isn't going to stretch or compress, then theta is the only coordinate that we need to describe this system. Now, if you had, for example, maybe a pendulum that could not only swing about some angle, but it also by some amount x, then we would need two coordinates. So our set of coordinates, which we'll just call q, is going to be x, how much it can stretch and compress, and the angle theta. So if we use these generalized coordinates, it's going to simplify our problem a lot. Now, the main restriction on these generalized coordinates is that they're going to have to be independent of each other. So like in this example, if you move in the x direction, you're not moving in theta at all. And conversely, if you're moving around in theta, you're not stretching or compressing at all. So mathematically, what we could say is that if we took the dot product of these two differential vectors, then they have to be zero. So if we took a tiny change in x and dotted it with a tiny change in theta, then it should be zero, because they're perpendicular. And as you may know from introductory physics, the expression for work is going to be that integral of the force dotted with the displacement vector. So our constraint forces, so going back to that simple pendulum example, if it can't stretch or compress, there's got to be some tension in this string directed this way to make that happen, to counteract that force of gravity. But if it's moving about in theta, then this constraint force is perpendicular to the motion, and the work done is zero. So if our constraint forces aren't going to do any work, so if they're perpendicular, then they're not going to do any work because their dot product will be zero. And likewise, if the force doesn't act through any discernible distance, so if you have, for example, a collection of gas molecules in a box, if the collisions between the gas molecules in the box just simply change the direction. So in other words, they conserve energy and momentum so that they're an elastic collision, then since that box isn't expanding or compressing, then that force although it is acting, it's not doing any work because the box itself is not expanding or contracting. And if we want to use these generalized coordinates, they're going to make our problems a whole lot easier in general. So now we actually get to talk about the principle of least action. And the principle of least action states that between any 2 points in time t0 and t1, the path that a system will take, so in other words, how those coordinates in our generalized coordinates change, is going to be the one that minimizes this thing called the action. Now, what exactly is the action? Well, I'm glad you asked. The action is going to be given by this integral right here. But what is this integral? Well, this function L right here is called the Lagrangian of the system. So our Lagrangian, if we have a conservative system, which is going to be our main concern, because at the most basic level, all systems are going to be conservative. Like that collection of gas molecules in a box, if you look close enough, all those collisions and everything are going to be conservative. So the conservative system is going to really be our main concern, and we'll expand more on this idea in future videos. But the Lagrangian will take the form L is equal to T minus V, where T is the kinetic energy of the system and V is the potential. Now, it seems kind of weird having an integral law like this, because does that mean the particle or system is thinking about all the different routes it could take? Unfortunately, the answer is no. It just happens that if you make this choice for your Lagrangian, you pretty much get Newton's laws right back out. So it's not so much that the system is doing calculus or looking at all the different possible paths it could take. It just does it because it's equivalent to Newton's laws. So if anything holds in Newton's laws, it's also going to hold in the Lagrangian formalism. So, sorry I had to burst your excitement there, but this formalism is going to end up being a lot better, however, than just using Newton's laws, because first off, this doesn't depend on the exact coordinates used. So our kinetic energy minus the potential at any point in time, no matter what coordinates you use, that kinetic minus the potential is going to have the same magnitude. Now, it may look a little bit different depending on the coordinates that you choose, but it's going to have the same magnitude. So we would say that this law is invariant under your choice of coordinates. It doesn't matter which one you use, you'll get the same equations out. So now, we have this integral law, but we want to turn it into a differential one, so that for any particular set of coordinates that we use, it's going to be the easiest one. We'll go over in future videos on if you don't use generalized coordinates, but under the assumption that you're using generalized coordinates, the equations of motion actually pop out pretty fast. So, from the last video, we actually derived what's called the Euler-Lagrange equation for a functional of the form f of x, y, and y dot, which is what we have right here, just with different letters. Our Lagrangian is a function of q, so any of those position coordinates in our set of generalized coordinates, its time derivative, and possibly time. Now, for a conservative system, which we'll show in the next video, the Lagrangian won't be a function of time. So, we pretty much have the same thing here as we do here. But in this case, Q, so we would say Q gets mapped to Y, Q dot, well, that's just the same thing as Y dot, because these are the dependent variables, and the independent variable in our Lagrangian is T, and it's going to get mapped to the independent variable in here, which is X. And we saw that the Euler-Lagrange equation looked like this. So if we substitute y for q, y dot for q dot, and t for x, we just Euler-Lagrange equation for the system. Now, what if we have more than one generalized coordinate, like in that spring pendulum example? Well, this is the beauty of using generalized coordinates, because if you use generalized coordinates, that those differential vectors had zero dot product. What does that mean? Well, it means mathematically you can just add up all your different equations, and they're going to be what we call linearly independent. They don't, you can't just multiply one equation by another equation and add two different equations to get another one. You can't do that. They're all going to be independent. And that's the true beauty of using generalized coordinates. Now, in this video so far, it seems like this equation right here looks just horrible. And the first time I saw it, I thought that too. I was like, yeah, that looks disgusting. But I promise it's not. And the main reason for that is that our Lagrangian is going to be T minus V, which is just the energy of the system. Well, the kinetic energy minus the potential. But we're messing with scalars instead of vectors. And in introductory physics, vectors, you may remember, are pretty hard. So we're going to simplify mechanics a lot by using this formalism. Because if you can write down the energy of the system, then all you have to do is take these derivatives and you have your equations of motion. Now, you probably are skeptical of that, so in the next video, we're going to start going into examples of how to use this equation. So, let me know if you enjoyed this video. Leave a like or comment in the comment section. See you next time.